Yu-Xiang has done some very interesting works on off-policy batch data reinforcement learning.
All right, thank you very much, Mengdi, for the introduction. I'd like to thank the organizers for putting together this excellent program. I have learned a lot over the 2 days of attending the workshop. So today's talk is going to be on off-policy evaluation, in particular with offline data and no access to the online environment. And what's probably different from a typical study of such problems is that we're going to be considering the uniform convergence in this problem on the very narrowish setting, but we hope that this setting will reveal some of the intricacy of the problem. Right, so this is going to be based on the joint work with my student Ming Ying and my collaborator Yu Bai from the Salesforce research. Yeah, so there might be like a subset of the people who have heard this talk at the RL series seminar that has been an excellent platform. So this talk will not have anything new. So I'm just saying that so that you know, like you can decide whether you want to leave now. All right. So all right. So the talk is going to be about reinforcement learning, obviously, and it's one of the hottest topics nowadays. And I just wanted to point out that most of the successful applications of reinforcement learning are in a scenario where you actually have access to a simulator. Say in games, you can run exploration for as many times as you want, as long as you have a sufficient amount of computation, right? However, in practice, what often happens is that when you want to apply RL, like you're left with a situation where you have some legacy data that's collected from like running other policies or from human taking actions in the environment and so on, and you don't actually is legally allowed to operate on the real task environment. So what can we do? Okay, so I guess the problem can be broken down into two parts, and that's also like the two main topics of today. So that's offline policy evaluation and offline policy learning. So in offline policy evaluation, we need to say work on evaluating like a given target policy that's stated independent to the data, and then design methods to use offline trajectories that's collected by a login policy called mu and somehow evaluate the value of this target policy. And offline policy learning is a more challenging task that would like to use the same data to directly identify the near optimal policy pi hat star, so that the value of pi hat star is similar to the value of pi star, which corresponds to the optimal policy globally. Okay, so there are multiple approaches of doing either of these tasks and for connecting the task 1 to task 2. But the version that we're going to be taking is to use like a more global approach of uniform convergence. So by deriving the uniform of policy evaluation, then that naturally implies that we can use any algorithm that works with the OPE estimator to somehow obtain a near optimal policy. Okay, so there are many applications of this. So what I wanted to highlight is that in all these applications, sample efficiency is actually hugely valued because it's important to make sure that every sample matters, and we'd like to make really design like efficient algorithm up to constant, such that we can leverage all the data that's available to us in cases such as medical treatment. And in places where exploration and actually accessing the tasking environment is costly, and this is like really the top priority to come up with algorithms that are statistically efficient, that in the sense that it's not wasting data on a per instance matter. And Martin's talk yesterday have motivated this problem quite a bit. And I'd like to just refer people who haven't seen this talk to watch Martin's video. All right, so here's what I'm gonna do. I'm gonna first spend some time to talk about the problem setup, and so we are all on the same page, and then I'm gonna talk about our contribution to the problem of offline learning, reinforcement learning with both the OPE and OPL. And then I'm going to talk about how these two are connected together and through the uniform convergence theorems with several interesting policy classes of interest. And if time permits, I'll end with some discussion on the technical components and how we derive this uniform convergence bond, and then share some open problems with the group. All right, so we're going to consider a very modest setting. So comparing to the previous talk, which is like a fully general scope of the offline learning problem, we're going to consider arguably the narrowest possible setting, so that we can have talk about concrete sample complexity and concrete optimal dependence and all the parameters of the problem. So we're going to be considering the tabular MDP in a non-stationary, or often known as time inhomogeneous setting, and to explicitly talk about the planning horizon, we're going to assume episodic MDP with a horizon being H, right? So non-stationarity says that the transition kernels might be different at different time point. And the corresponding policy and then the expected reward vector are also going to be different at each time point. So this is just slightly more general, and certainly algorithms that operate in this setting can be applied to the stationary case with a loss of factor of H in terms of the sample complexity. All right. And there's standard value function indexed by pi and indexed by t because it's time inhomogeneous, and standard definition of the Q function. The only thing I want to say is that we also define this scalar v pi, which is the single variable, single number description of the value of a given policy pi, right? So the initial state is like arbitrary. It's either drawn from some distribution or specified as a fixed state. The data, so the key difference from other consideration, other existing studies of the offline RL is that we're not assuming access to a generative model. So we actually have like n trajectories of executing, of rolling out on these episodic environments. Just like the previous talk, we need to talk about the marginal state action visitations, with the difference being that now this is indexed by t, right? So we can also conveniently define this matrix of state action transition matrix given by a particular policy pi, right? So this is a SA by SA matrix that we can simply apply these matrices to the state action distributions, so that we can simulate the Markov's mixing dynamics. All right, so just one disclaimer. So exploration is often the hardest problem in RL, but since that we're working with offline RL, we don't have to deal with exploration. We can simply assume it away, right? Because this is mostly because by construction, the logging policy that we use to collect the data is out of our control. So all we can do is to assume some properties that is satisfied and then try to work out the best bound that it entails us to do, right? So the specific assumption that we make is a somewhat standard one. So it's basically that the logging policy is going to visit every state action pair at every time step. And as long as there is a policy in the policy class of interest that we want to derive uniform convergence, has a probability that's greater than 0. So it's like a measurability assumption, and then like in some sense this is without loss of generality, and you have to assume some sort of conditions like this in order to argue that you can identify the optimum policy. Okay, yeah. So I'm gonna like start by making two observations on the high level of the problems of off-policy evaluation and learning. So first of all, I claim that OPE is essentially a statistical estimation problem. Like it's like, even though it is in reinforcement learning and there are dynamics and so on, it is a standard statistical estimation problem that we'd like to estimate a single unknown quantity v pi using the observed IID data. Okay, so it's slightly non-trivial due to the underlying dynamics and due to the many nuisance variables that are available that we have to estimate. But if all the techniques from statistical estimation can be applied here, and we can hope to get statistical efficiency if we use these techniques correctly. Okay, we can either talk about a high probability error bound, or we can talk about the mean square error as a standard approach in statistics, and yeah, hopefully that's a much easier problem. The second observation that I'm going to make, like I don't really have to say this because this is already covered by Nam from the previous talk. So offline learning is essentially a statistical learning problem. Okay, without online access to the environment, so you are using IID samples of n copies. So they are somewhat structured, but they're IID samples. And you're given a policy class or a hypothesis class in which you wanted to identify the optimal policy, right? So they're agnostic learning where you don't assume the hypothesis class captures any information about the distribution. There are also other assumptions that you can make, such as realizability, and more assumptions to make the problems more tractable. So so that allows us to take some lessons from statistical learning theory that which says that it suffices to run empirical risk minimization. It is sufficient and necessary to use empirical risk minimization, and any learnable problems are also learnable with ERM or asymptotic ERM. In the context of RL, this is saying that we can simply design some kind of estimator. We had pi, some kind of OPE estimator, and then just do exhaustive search, right? So how you implement this argmax is out of the picture, but we're interested in the statistical property of such ERM estimator, which seems to suggest that we can simply evaluate pi and also evaluate pi hat that comes out of this ERM, and that gives us a 2 epsilon upper bound of the suboptimality of offline learning. So we since this is a theory group, and from the statistical learning 101, we all know that this is a flawed argument because pi hat is data dependent. So what we really need is a so-called uniform convergence. So if we are able to add just an additional thing, add a supremum over a family of policies, so the high probability holds like simultaneously over all policies within this policy class, then this argument works, and then we can use uniform OPE to derive the offline learning bound. With the advantage being that this is algorithm independent, so you can use any algorithm that optimizes the empirical objective, and that will give you like the same bound for offline learning relative to the uniform of offline policy evaluation. All right, so there are some blow up in the parameters in terms of the sample complexity. So from the standard statistical learning, so this is typically given by some complexity measure D, right? So this could be the number of parameters, or more generally VC dimension or the metric entropy. And for finite policy class, so like usually this is relatively on the same order of the log of the cardinality of the function class. You can also use Rademacher complexity to derive such uniform convergence bound. Okay, that raises an interesting question. So, what is a natural complexity measure for the policy classes that's commonly used in reinforcement learning? So today I'm gonna give like some preliminary result on this of this problem on the standard tabular MDP setting. Okay, so a short summary of our key contribution on the two problems. On the problem of pointwise offline policy evaluation, so our results says that you can solve this problem where analyze the mean square error with this complicated looking expression. So if we simplify this a little bit, well, so it scales with h square over h square over n ndm. So ndm is the like so dm is in the best possible scenario is relatively on the order of 1 over SA. So so you can see like it leads to a more interpretive bound. And one thing I wanted to also point out is that the leading term in this expression is also the Kramer-Rao lower bound. So essentially, we have completely solved the at least asymptotically the OPE problem, the pointwise OPE problem, because it matches the lower bound for every pi, mu, and MDP pair, MDP triplets. On the other hand, for the uniform OPE, we've derived a set of results that allows us to show that if we just use the model-based estimator and then plug in the estimator to estimate the empirical MDP, and then say use value iteration or policy iteration to find the optimal policy, then this ERM obeys strong properties that it achieves the sample complexity bound error rate that with just a blow up of a factor of h in the square root, and we also showed that this quantity is information theoretically optimal. Okay, so that's a summary of the result. So I won't go into the details of the prior results. So but there are a long line of work on both problems. More on the offline policy evaluation with the first work of such starting from the standard simulation lemma. But you see that we've made some substantial improvement over the parameters and end up reaching the optimal result. The one thing that I wanted to point out is that the same result is also implied by Mondi's work that focus on linear MDP, but it implies the optimal sample complexity with high probability of the same order, and they are also per instance optimal. For the problem of offline policy learning, the picture is a little bit more complicated because we don't really have a good comparator on the same setting. So the closest to us is the work of Xie and Zhang, which deals with the infinite horizon setting. But if we translate the result to our setting, then they get an additional dependence on H on the planning horizon. So the concrete comparison is really the simulation lemma, because the simulation lemma is actually a uniform convergence bound rather than a pointwise convergence bound. Although like it suffers a deficiency of a factor of blow up on h square h times s square. Okay, so there are also comparisons with respect to settings that assumes a generative model, which is more well studied. We've actually learned some useful techniques from this literature to derive our tight bound. So we can see that there are some improvement over these approaches as well. So there are method-specific algorithms. These bounds apply to specific algorithms, and there are also like similar uniform convergence type of bounds that applies to all methods that gives you the nearly empirically optimal policy. So this epsilon opt is the optimization error. So if you run your algorithm forever, then you can get you can get this to 0. Well, we made some improvement over the tightest bound in the generative model setting as well. Okay, so that's a summary of our main contributions. I guess our result is first it achieves optimal rates in the offline setting, and there's a matching lower bound that we prove, which explicitly depends on the exploration parameter DM. So the construction is like takes a few clever thoughts, but is more or less the same construction from before, tailored for this particular setup. Okay. Right, and we've come up with examples to demonstrate that this H cube is really the right scaling. So what this is saying is that if we want to answer the question is that what is the right complexity measure for reinforcement learning problem, for offline reinforcement learning problem, then that quantity D is really the planning horizon H under our model. So this is an interesting observation because like usually like in the previous talk, we consider the policy class or the family of finite family of value functions, and then it is typically considered that the log of the cardinality of the policy class is the right objective to achieve. But at least in this case, if we use a union bound, this will give us additional dependence on a factor of H, a factor of S. But our lower bound actually expect that we shouldn't really depend on the size of the state space. Okay, so if we use most standard techniques to deal with this problem, we'll end up leading us to something similar to simulation lemma, which have additional dependence on H and S and so on. The part of the reason why the dependence on H is tricky, even for the pointwise estimation problem, is because, say, if we look at this primary raw lower bound, so it's a summation of H quantities that can be as large as H in every item. So if we sum this up, so we somehow magically get H squared rather than so this is on the this is typically on the order of H squared. So we're summing like H items with the maximum value being H squared, but we magically end up getting H squared without blowing up over the summation. So this is sometimes handled by the law of total variance, and there's a cute proof that for the offline and off policy case, like in our previous paper at the stats. All right, so now let's get to the uniform convergence and how we actually get the offline policy optimization bound. So we consider three families of policies: the family of all policies that applies to this problem, and the family of all deterministic policy, and finally we consider a local policy class called epsilon opt empirically optimal policy pi hat, which says that the value of this policy pi is close to the empirically optimal policy. So by empirical, it means that we are evaluating this quantity according to the empirically estimated MDP rather than the unknown like true MDP that generates the data. Okay, so if we can solve the problem with even the narrowest class with uniform convergence, that implies an offline learning bound with the same error rate. Okay, so for the global uniform convergence for all policies, so this is what we end up getting. So we get a result that has a right dependence on N and Dm, but there are a blow up factor of H here, and a blow up on the factor of HS on the second term, but notice that there isn't a log 1 over delta. So when delta is extremely small, then we can subsume this into the bound, and then we get something that's only a factor of H away from being optimal. Okay, so I won't bore you with the details. It requires some martingale decomposition and a lot of statistical tricks and concentration and Rademacher complexity argument and application of Mark-Diarmi inequality to get this bound. So for the family of all deterministic policies, and using the similar technique before, we can, or just directly using Mondi's work, we can apply union bound to the high probability of policy evaluation bound, which gives us a blow up of HS over the H square pointwise convergence bound. But this bound is suboptimal by a factor of H. So finally, if we consider a family of empirically near optimal policies specified by this policy class, then there are some tricks that we can use to somehow like decouple the dependence between the past and the future by after conditioning on the number of like state Gaussian visitations that we observe at any given moment, and that allows us to derive a conditional version of the second like tricky issue that we discussed earlier, that sums up the conditional variances into H squared without introducing additional dependence on H, and that saves another factor of H, and which leads to the bound that matches the information theoretic limit. Okay, so so that's three of our like uniform convergence theorems. So I like really won't have time to talk about these techniques in the proof, but some of them might be applicable to problems that you are working on for both offline RL and online RL. We have a martingale decomposition of the error, of the empirical error, that have two forms, both a primal and dual. We have a fictitious estimator technique that allows us to deal with the tricky dependencies that's given by the offline setting rather than the generative model setting. The idea of anchoring around the empirical optimal policy after taking a difference of the empirical estimated Bellman equation and the true Bellman equation. So this idea is coming from Argawa, Kakade, and Yang, Argawa, Kakade, and Yang, and we've made some improvement to this technique that allows us to apply this to our problem and achieve better dependence on certain parameters. Okay, so for people who are interested in this, you can ask me offline or just look at the paper. Okay, so to reiterate the main point, we've derived uniform pointwise and uniform convergence results for the offline evaluation problem. For the pointwise problem, we have obtained in some sense the best like per instance optimal results after low order terms. And for the uniform convergence result, we've derived the rate optimal bound that satisfies this for all practical reasons of policy optimization for identifying the optimal policy. Getting these tight dependence on all the parameters is non-trivial, and some of the proof techniques might be generalizable to other settings as well. Okay, so I'd like to conclude the talk by stating a few open problems. So first of all, like even in this very restricted setting of tabular MDP, the rate of global uniform convergence is still unknown, right? So our conjecture is that it is as expected, as the same as our lower bound, but there are technical issues in actually deriving this, and we're actively working on that. There are some promising leads, but I still think that we need some additional like new insight to completely solve this problem. It's natural to think about what is a natural complexity measure beyond the tabular case, and say for the policy classes such as the softmax policy for those that are natural for proximal policy iterations and so on. And to generalize this problem to functional approximation, because if we really want to apply reinforcement learning to real life applications, it is important for us to get efficient algorithms, which means that like including handling the implicit dependence on all the parameters of the problem that's hidden within the policy class, the log of the cardinality of the policy class. Okay, thank you very much for your attention, and here are the papers.
Great, thank you, Yu-Xiang. Very solid work. So I follow both Yu-Xiang and Nan's work very closely, and I think that this set of results are very strong. And certainly, I think like being able to make the connection between important sample and making the optimal, this is definitely a non-trivial contribution, and set the tone for a lot of follow-up works. So thank you. So do we have any question for Yu-Xiang and Nan? So there was a question in the Q&A from Chaba. I think that's question to Nan. Maybe Nan, do you want to answer that?
Modi, shall we start with Yu-Xiang's question since he still has slides here? I think Chen and Amir Masood both have questions for him.
Oh, sorry. Where's this questions?
In QA. In QA.
Oh, I see. Sorry, I didn't see
that.
Yeah.
I'll just let people grill Yu-Xiang first and then forget about my talk.
Okay. Chen, can you speak? Sorry, I didn't see your question earlier.
Yeah, I'm looking at it. So Chen's question is, what does near empirically optimal mean? Yeah, sorry, I should have explained that more clearly. It means that it is empirically optimal with respect to the estimated empirical MDP. Right, we're taking a model-based approach. And for the next question, so the bound of the policy class is nearly optimal with respect to empirical optimal reminds me of local Rademacher complexity and the peeling argument in the empirical process theory. Like, have you used any of these techniques? Do we really need a global uniform convergence as opposed to the focusing on the policies that are more promising? Right, very interesting question. So, the first question: are we using local Rademacher complexities and peeling arguments? Not really. On top of my head, I don't see how they are directly applicable here. But certainly we can look closer, look more closely into this. And do we really need a global uniform convergence? I guess from a policy optimization point of view, like not really. On the other hand, like in the offline learning in practice, typically we don't expect to get to the global optimal solution like one shot, right? So what we can hope to do is to maybe improve the policy a little bit. So there are many heuristic algorithms and the evaluation functions that are heuristics that you can use to solve the planning problem. So I think it is still important to allow global uniform convergence, and it would be great if it has the same rate. In a sense that then that will allow any heuristic methods for you to run, and then what you see on the empirically estimated MDP is going to be what you get on the population level MDP. All right, yeah, I guess if there are no further questions, I will just pass the mic to Nan.
Amanda, like, I thought you wanted me to clarify some question from Chapa, but I mean, we had a somewhat long conversation in there. I don't know if there are any particular parts.
Yeah, I thought that's even the first question is good, right? Because like it's easy to think that state aggregation in Q star is similar to linear MDP, but it's actually a much more general setting, right? So would you like just explain more?
Actually, I'm not sure what's the best, the sharpest message here, but I think Chapa is trying to draw a connection. Sorry, Chapa is trying to draw a connection between state aggregation and linear MDPs. But I think first, the state aggregation within itself, there are many versions. And also, I think none of the versions correspond to exactly linear MDP. For example, as I put in the chat, the bisimulation is sort of like different. Linear MDP says that your transition matrix have a low rank factorization, but bisimulation, when your problem has a non-trivial bisimulation, that's not necessarily true. That's first. And second, in my work, I didn't use bisimulation. I only used the Q star relevant abstraction. And as I showed in the slides, for any arbitrary MDP, even if your low rank, your transition matrix has like ridiculously like weird structures, the complexity Q star relevant abstraction always exists. So I think they're related, but they're not the same thing. Yeah.
Okay, thank you, Nan. I think we have to let you go. All right, let's thank Yu-Xiang and Nan again for the wonderful talks and their very strong results. And we appreciate that you presented clearly in our workshop. Thank you. Okay, so I hope to see you again in the morning tomorrow. And so that's all. Thank you all for participating.